In day 3 of the 8.2, 8.3 notes, we're going to look at the traditional method, which is another way to evaluate hypotheses that doesn't use p-values. In this example, we have a drug company who's developed a new flu vaccine. The company claims that less than 5% of people who take this vaccine are going to develop the flu. Researchers want to test this, so they give the vaccine to 1,000 people, and they find that 43 of them get the flu. To find the parameter, P is going to equal the true proportion of vaccine recipients who will get the flu. And the hypotheses, it's based on this statement up here. The company claims that fewer than 5%. So that's what we want to prove. We want to prove that if you take this vaccine, there's a less than 5% chance you get the flu. Null hypothesis, P equals 0.05. Alternative, P is less than 0.05. Next up, let's find the standard deviation of this sampling distribution. It's based on the null hypothesis value because we're assuming this null hypothesis is true for the entire test. So we're going to plug in 0.05 for the P, 0.95 for the Q, 1,000 adults, that's our sample size. We get a standard deviation of 0.00689. Test statistic is a Z-score, and it's how unlikely was it that we saw 43 out of 1,000 adults. Okay, that's a p-hat of 0.043. Is that unusual if this is true? So we put that 0.05 right in the middle of our curve down here. We're going to use this standard deviation. How unlikely would it be to get 0.043 or less? If that's true, we get a z-score of negative 1.16 based on these parameter values. Now, when we use the p-value method, at this point, we would take that z-score, we would look it up in our table and get a probability, a p-value for that z-score. This time we're using the traditional method, and it cuts out the p-value. So we want a critical value. It's based on an alpha level, which isn't given in this problem. So we're going to default to 5%. That's always what we use when we don't have an alpha level. Okay, that's not from the null hypothesis. It's just the standard alpha level. So we would put that 5% on the left side of the curve. It's the left side because we have a left-tailed test. Our alternative is saying, is P less than 0.05? So we have 5% over here. This is what we're looking up in the middle of our normal distribution table to get a z-score. We get a z-score of negative 1.645. So really what that's telling us is that the cutoff for 5% on the left is a z-score of negative 1.645. Okay, now we want to put our test statistic on this graph. So we just found that test statistic was negative 1.16. We have 0 right in the middle of our curve here. We got a negative 1.16. That's not quite in this area right here. So let's say we put it like right here. Okay, the key thing about this test statistic is it's not in the shaded region. And because of that, we are going to fail to reject the null hypothesis since that test statistic is not in the critical region. Thought about another way, if we get a z-score that's farther away from 0 than 1.645 is, let's say it was negative 1.98. Okay, if we looked that up in our table, we would get a p-value that's less than 5%. We would reject the null hypothesis. That's not what's happened. Okay, we got a z-score that's closer to the mean, closer to 0 than 1.645 was. Okay, it was 1.16 negative. That would give us a p-value greater than 10%. We would fail to reject the null hypothesis because that p-value was larger than alpha. Okay, but we're just cutting the p-value out. And we're looking at that critical value of 1.645. If it's in that tail that's shaded, we reject it. In this case, it's not. We fail to reject. Conclusion. We always write the conclusion based on this alternative hypothesis. In this case, we don't have sufficient evidence to suggest that the proportion of vaccine recipients who will get the flu is less than 5%. We would need to see a farther difference than we did, than 43 out of 1,000, or take more data, and that might move this z-score far enough over where we can reject. Next example. It said that coffee drinkers preferred fresh brewed coffee over instant coffee. There's a skeptic. He says, no, that's not true. At most, half of coffee drinkers prefer fresh brewed coffee. Everybody else just wants caffeine. So he takes a sample of 50 coffee drinkers. He randomly assigns them 1 of 2 cups to drink first, either fresh brewed or instant. They taste both of the cups in that random order. They decide which one they like. 36 out of the 50 chose the fresh coffee. Parameter. P equals the true proportion of coffee drinkers who prefer fresh brewed coffee. Hypotheses for this one are a little tricky. It has to do with this sentence here, at most half. So at most half means up to including 50%, 50% or less. So we have less than or equal to. If it has an equal sign at all, it's the null hypothesis. So our null hypothesis is that it's equal to 0.5. The alternative is going to be the opposite of this, or greater than 0.5. Standard deviation, based on that null hypothesis value, 0.5 times 0.5 over 50, square root, and we get 0.0707. Test statistic, the p-hat, 36 out of 50 is 0.72. Would that be unusual to see if the actual true proportion of coffee drinkers who prefer fresh brewed coffee is 50%? So is this unlikely to end up with 72% or more than that? Z-score for that is 3.11. Critical value, again, it doesn't give us an alpha level, so we're going to use 0.05. And this time it's a right-tailed test. We want to see, does P equal something that's greater than 50%? So we're going to put this on the right, 5% on the right. When we look this up in the table, remember we always look up area to the left of this. So 5% over here means there's 95% over there. We look up 0.95 and we get 1.645. Z-score was 3.11. So our critical value is 1.645. That's the cutoff for this line right here. And our test statistic was 3.11, which is out here. In this case, our test statistic is in that shaded region. Because it's in that shaded region, we're going to reject the null hypothesis. When we write our conclusion is always about the alternative hypothesis. Since we rejected, there is sufficient evidence to suggest that the proportion of coffee drinkers who prefer fresh brewed coffee is above 50%. If that confuses you, another way to look at it is if the null hypothesis is true, and if 50% of coffee drinkers at most prefer instant coffee, right? The probability that we would see 72% in a sample of 50 people, okay, or even more than that, is really small. It had a Z-score of 3.11. So if we were to look that up in the table, we would see that has a really small likelihood of occurring, which leads us to the conclusion that this is actually not true. We're going to reject that, and we're going to conclude that the alternative hypothesis is true. The alternative says that the proportion is actually greater than 50%. When it comes to those last two steps, the final two sentences where we make a decision and state a conclusion, they're tied directly to our test statistic and the alpha level. So we look up that alpha level in the normal distribution table, we get the cutoff, and we shade from that cutoff out to the end tails of the distribution. If our test statistic is in that shaded region, first sentence, we reject the null hypothesis because it's in that shaded region. Second sentence, there's sufficient evidence to suggest that the alternative hypothesis is true. If the test statistic is not in that shaded region, we fail to reject the null hypothesis and find insufficient evidence to suggest that whatever the alternative hypothesis is true. That first sentence is always about the null hypothesis. Either we reject it or we fail to reject it. The second sentence is always about the alternative hypothesis. Either we have sufficient evidence to support it or we have insufficient evidence to support it.